Hi, right now, I'm going to work through the additional problem solutions for topic 15, annuities. So let's go ahead and see what those are. As you saw in the video, we're only introducing annuities. We're not really going to get into a lot of the stuff you can do with annuities, but just the little bit we're going over is actually very useful, and maybe it may actually be very useful for you even in your personal life. It certainly is something that you will encounter, these concepts, and it's helpful to know how to do some of this math. So, um, what we saw in the topic 15 lecture video for annuities is that the future value of an annuity, so the future value, which is like the accumulated amount, we just tend to call it future value. That's just what's done. Um, is this sum that we derived in the video. Um, And this quantity, you actually don't have to have it memorized, this formula. I'm going to provide it for you, but you do need to know how to use it. So it's this result of a geometric progression, the sum. And as you saw in the video, the lecture video, it's this R, which is the amount that we pay into the annuity on a regular basis. And it's 1 plus I raised to the n minus 1 all over I. Okay, so that's the formula we're working with for these problems. So let's go back and, sorry, I wanted to make that big. So here you go, you can see it big now. So this formula is the main formula in topic 15. It is the annuities formula, and it is derived from the compound interest formula, as I already showed you. So let's go in and see what these problems tell us to do. And they're all basically the same thing. So once you get the hang of it, I think you'll be more comfortable with it. So let me share that problem again. Here we go. So for the following problems, find the amount, the future value of each ordinary annuity. So if you remember from the lecture, I talk about annuities being ordinary. It means that they are going to accrue interest in accord or at the same time. You make payments at the same time that you accrue interest. So if it's compounded quarterly, you make payments quarterly at the end of the quarter. All right, so this first one is saying to us that we have $1,500 being deposited or paid semi-annually. So let me put a little dollar symbol by the 1,500, semi-annually. For 8 years. So our time is going to be 8. And at 9% interest, nominal interest compounded semi-annually. So our rate is 0.08, and sorry, I got that wrong, 9%, 0.09, and it's compounded semi-annually. So that automatically tells us semi-annually, remember, is twice a year. So that's 2. All right. So now that I did this, let me make this whiteboard big so we can see it. All right, so let's go ahead and figure out how much we have. Well, in this formula, we see that we need an I and an N. We're not given I's and N's, so right, this I and N hasn't changed. It's the same as it was before. It's the rate, the nominal rate or the annual rate, divided by the number of conversion periods in a year. So for a semi-annual rate, that would um, semi-annual compounding, that means we're going to have 2 conversion periods in a year, right? So every 6 months. So our little I, the interest rate that applies for that conversion period, is 0.09 divided by 2, or 0.045. All right, then the next thing we need is the N, and the N is the number of times this is going to happen, how many payments we make, or is one way to think about it. Or another way would be the number of conversion periods over the time of the term, and the term here is 8 years. So it's 2 times 8, or 16. Okay, So our total sum is going to be 1,500 which is our um, payments that we're making in twice a year, or not we, whoever's doing it. And we can put, there's no difference, right, between the square and the round brackets, but it just makes it easier to see. We have 1 plus the I is 0.045. And now this little exponent's inside this big bracket, it's a 16. And then we have a -1 outside the whole thing. And we divide the whole thing by 0.045. All right, so what you want to do is make sure that you can match me um, on your calculator. I know different calculators, you input this differently. So that's the part that you need to practice and make sure you get it right. So if you're lucky and you have a good calculator, you can just type this in 1,500 times open bracket, and then maybe another open bracket for the whole numerator, another open bracket for this 1 plus 0.045, close that bracket, raise that to the 16th, subtract 1, close the bracket for the numerator, then divide by 0.045, and then finally the final close bracket. So you just have to keep track that you have the same number of open brackets as closing brackets. So what I just said was, if you're using a calculator and you're trying to make sure you put this in right in your calculator, you might want to add an extra bracket just for the numerator right there. And actually on a calculator be an extra parentheses, right? Because that's what they use. All right, so if you did this, and I'm going to go ahead and do it on my end. With my iPhone calculator, I have to actually start from the inside and raise that to the 16th. And once I have that, I subtract the 1. And once I have that, I divide by the bottom. And I get a number that's like a 22.72. And I'm going to multiply that by the 1,500. And I end up with 34,079. And if I round to the penny, I get it's 0.005, so it'd be 0.01. So 1 penny. All right, let's do the next one. So here we're going to put 600 per quarter. So our R, I should have said that was R up here, is going to be 600. Our payment is 600 per quarter. And because it is an ordinary annuity, we know that that means we're going to be also compounding interest quarterly. So it's going to be for a term of 9 years. And the rate, the nominal rate or the annual rate is 12%. So that's a 0.12. And we know we're compounding quarterly because we make payments quarterly and it's an ordinary annuity. So that means quarterly means our number of conversion periods is going to be 4. Okay, so let's go into the big screen. All right, so at this point, we're just going to go back to this annuity, future value annuity formula. So the total, the future value, the sum of that progression is 600 times 1 plus, and our I, we didn't calculate our I yet. We can come over here and do that. I'll do it in blue. So using, remember I is going to be the R, so 0.12 for 12% divided by 4. Okay, so that's going to be 0.03. And the other thing we're going to need is the N. So let me get the N. We can put that in a different color. So N is going to be MT, M times T. So 4 times 9 or 36? Okay. And just to keep things nice and clear, let me put a line that this is all problem 2 that we're dealing with, so separated from problem 1. Okay, so we're going to put 1 plus our I, which is 0.03. We're going to raise it to the nth power, which is 36. We're going to subtract 1, and then the whole thing is going to get divided by 0.03. All right, so let's see what this ends up being. And we're going to have a dollar sign. And by the way, on the bright space, on the assignment 5, you do need to put the dollar sign as part of your answer. You can put a comma or not a comma, and that shouldn't matter. All righty, so let's go ahead and see if we got this right. All right, so once again, I have to do this 1.03, and then I have to raise that to the 36. And hopefully you have a better calculator than me. Then we're going to subtract 1, and then we're going to divide by 0.03 on my end. And then I multiply that whole thing by 600. So you might get to type it in from left to right, just the way the way I wrote it on the whiteboard. So what I get is that this comes out to be, where's my pen? 37,965 and 57 cents. By the way, a good question to think about or to be aware of. It's not really asked so far in anything I've covered with you, but a good question to kind of know is, well, what happens if you didn't do this? What happens if you just put this money in like an envelope under your bed or something? You would have been putting in 600 a quarter for a total of 36 times, right? 9 times, 4 times a year, or 36 times. So what's 36 times 600? And that'll tell you how much more money. This would be the total showing how much more you made by putting it into this annuity. Let's just look at that real quick. Sorry, my phone seems to want to lock up. All right. So let's do 600 times 36. And that comes out to 21,600. So you see, we made a lot more money by putting it in this, or whoever did this, made a lot more money than the 21,600 they would have made if they had not done this and just put it in an envelope under their bed or wherever, by putting it into this interest-bearing annuity. All right. And that's such a big difference. I'm actually going to just double check my math here that I didn't type something in wrong. Nope, looks like it's right. Okay, cool. So that's problem number 2. Let's go on and look at problem number 3. All right, so now we're going to do some word problems. I'm going to go ahead and erase the board, except for the formula, because that's the only formula in topic 15. Okay. And this problem says IRAs. If a merchant deposits $1,500 at the end of each tax year into an IRA paying interest at a rate of 8% per year compounded annually, how much will she have in her account at the end of 20 years? So an IRA is a type of a retirement account, which is why we're talking about going out 20 years. So let's start problem number 3. We're talking about an amount being deposited of $1,500 at the end of each tax year. Okay, so remember, we're talking about ordinary annuities. So since we're talking about year, we're automatically going to have an M of 1 now. So the rate on this is 0.08, and it's compounded annually. So our M is equal to 1. And so we want to know that after a term of 20 years, how much has been accumulated in here. Okay, so let's go ahead and work that one out. So our sum is equal to the 1,500 times the quantity 1 plus I, and I, remember, is now 0.08 divided by 1, so it's just going to be 0.08. And our N is MT, M times T, and so it's just 1 times 20, or 20. So that's our exponent, minus 1, all divided by 0.08. So that on my calculator comes out to be 1.08 raised to the 20th minus 1 divided by 0.08. And I hit equal on my iPhone. If you're using an iPhone calculator, every time I do like one piece, I say equal, and then I take that equals, and then minus 1 equal, and then divide by 0.08 equals, and then times 1,500. That kind of keeps you from getting in trouble. So if I did it right, I get 68,642 and 95 cents. All right, so that's what this merchant has accumulated in her IRA after 20 years. So I'm going to just double check that again. 1.08 raised to the 20th. Oops. Minus 1 divided by 0.08 and multiply that by 1,500. Yep, that was right. Okay. So it's always good to double check on, especially all these numbers floating around in the calculator. Okay, next one up. Let's look to see what that problem is. So here we have a savings account question. So it's number 4. And this one says Jackson is going to deposit $100 at the end of each month. So we're talking R is $100 at the end of each month in a savings account earning interest at the rate of 8% per year, which is compounded monthly. Again, ordinary annuity. So it's going to how frequently he's making deposits to the savings account is going to match the compounding. And if we're talking monthly, we mean 12 times a year. Okay, so if we do that, then how much will he have on deposit at the end of 6 years? So the term is 6. So we want to know where we're at after 6 years, assuming he makes no withdrawals, of course. So let's go in and use our formula again and figure this out. So that amount is 100 times, we're going to need to calculate the I's and N's here. So let's do that over here. I is the 0.08 divided by 12. And that is I'm going to leave it like it's some number with a third in there. So we're going to leave it like that. And let's see, 100 times 1 plus 0.08 divided by 12. We're going to raise that to n. N is going to be the number of years, the number of conversion periods times the number of years. So it's going to be m times t, right? And that's 12 times 6. So 12 times 6 is 72. So we're going to do a 72 in the exponent. And we're going to subtract 1, and then we're going to divide by this 0.08 divided by 12, which I'm just going to leave in my calculator and see what we get. Okay. So go ahead and see what you get on your calculator, or maybe you already did all this. You're just checking your solutions. So let me do that. So I get $920.25. All right, so I'm going to do that again real quick because there's a lot of numbers in here. So 0.08 divided by 12 plus 1 equals 1.06666667. Raise that to the 72. Subtract 1 and divide it by, and now I use the parentheses, 0.08 divided by 12, close parentheses, and then equals. And I multiply that by 100. Oh, I got a different number. So that's when we need to be careful. Okay, let me double check now which one I get, which one was right. So 1 plus 0.08 divided by 12 equals, raise that to the 72nd power minus 1 equals, and divide that by the 0.08 divided by 12. And I get 9.2. So I'm getting a 9.2 something out of this part. And if I multiply that by 100, this number, I'm getting this number again the second time, 920.25. All right, so I think that might be right. So we can put a square around this. We should have been putting squares around these numbers, huh? All right. So the next one is going to be problem 5. So let's see what that says. Okay. Kyo accounts. Robin, who is self-employed, contributes $5,000 a year into a Kyo account. How much will he have in the account after 25 years if the account earns interest at a rate of 8.5% a year compounded yearly? All right, so let's gather that information up. The red is not erasing very well, so hopefully you don't see big red splotches, but let's gather what we know. All right, the contribution, the R, is 5,000 a year. And this is going to be for a term of 25 years. And the rate is 8.5 per year. So 0.085. And it's annual, so we know we have M equals 1. So that's always nice because it makes everything easier. We don't have to really do too much math for the I's and the N's. So the I is just going to be the rate divided by 1, and that's just 0.085. And the N is just the number is M times T, right? Sorry, kind of drawing sideways here. M times T, and that's just going to be 1 times 25, or 25. So our sum is 5,000 times this 1 plus 0.085 raised to the 25 minus 1 divided by 0.085. So let's see what that comes out to be. All right, 1.085 raised to the 25th minus 1 divided by 0.085 multiplied by 5,000. So I'm getting $393,338.96. Okay, and I'll just double check my math on this one. Yes, I matched it. So I think that might be right. Oh, this one I forgot to stop sharing. Sorry about that. All right. So let me go over that again. So the I is just the 0.085. The N is 1 times 25 or 25. We're going to plug into the formula 5,000 for the payments. And then 1 plus 0.085 raised to the 25 minus the 1, all divided by 0.085. And putting that in my calculator, I get 338 and 96 cents. Okay, so at this point, you have hopefully enough examples to do not only the homework for assignment 5, but to be ready for the quiz on Friday. All right, bye.